The second presentation is going to be from Korea. It's an automated checking of scaffold safety regulations using multi-class 3D segmentation. It's 51.
Okay, good afternoon, everyone. I'm Jeehoon Kim from Yonsei University, and today I'm here to talk about my research project, automated checking of scaffold safety regulations using multi-class 3D segmentation. And these are my co-authors. Sorry, my page is not. Thank you. So scaffolds are a temporary structure that is indispensable for a construction project. However, the scaffold is also a crucial factor in the occupational deaths in the construction industry. According to Korean Occupational Safety and Health Agency, almost 1/4 of the Korean occupational deaths in the construction industry are caused by scaffold-related accidents. Scaffold, because of its temporary status, is assembled and disassembled numerously even for a single project. And in this process, according to KOSHA, a human safety manager is supposed to check a list of regulations and whenever a scaffold is built and resumed after time and before being disassembled. This is often inaccurate and time-consuming, and the manager himself can be prone to accidents. For these reasons, we thought that automation of this process is needed. So for our research, we'll concentrate on automating the checking of these 3 regulations from KOSHA guideline on scaffolds. To add a bit more information for the regulation 3, the attachment status of guardrails also contains checking the distances between the guardrails. This is our overall framework. It can be divided into 3 big parts: point cloud data acquisition, multi-class segmentation, and automatic regulation checking by a role-based algorithm. Point cloud data acquisition is composed by Faro M70, which is a terrestrial laser scanner, and we acquired a total of 16 registered point clouds from 4 construction sites. 15 of them were from site A, B, and C, and those were used for train data, and 1 data from site D was used as test data. The acquired data is composed of X, Y, and Z geometric coordinates for each point, and you can see an example of our registered point cloud on the below figure. For the multi-class segmentation, we used a deep learning-based point cloud segmentation model called RandLanet. So RandLanet uses random sampling and local feature aggregation modules to efficiently and accurately classify large-scale point clouds. It also uses an encoder-decoder structure to make point-wide semantic segmentation predictions. And this model has proved to effectively extract small entities from large scenes by showing high performance on the semantic 3D dataset. And for the training of this model, we considered that our dataset was not large enough to effectively train the whole complex model. So we used the transfer knowledge from the semantic 3D dataset and retrained only the inner 6 layers of the encoder-decoder structure with our own dataset. So our dataset is labeled into 6 classes, which is stairs, work platform, guardrails, uprights, bracing, and background. So on the right figure, you can see an example of our labeled point cloud that is in our train data. And in conclusion, when a raw point cloud is inputted into our fine-tuned RandLanet, we get a prediction output for each and every point of the point cloud, one of these 6 classes. After the segmentation step, we now proceed to the regulation checking step. So first, we use the upright classified points from the RandLanet to find representative coordinates for each uprights on the XY plane. And using those coordinates, we determine the outer line information by finding the concave hull of the upright coordinates. And this outer line information is very important because we will use them as the baseline for searching work platforms and guardrails afterwards. Secondly, we use the work platform classified points to find representative z-values of each floor of a scaffold. We do this by a simple peak finding based on point densities. And after these two steps, we can now calculate 3D potential field of work platform and guardrails based on those informations. So a potential field is literally an area where a work platform or a guardrail is potentially existing. So you can see a visualized example on the right figure over there. And after those pre-steps, now the remaining steps of the rule-based algorithm is very simple. So this framework is a process for checking regulation 1 and 2. So using those process data from before, we now check if work platform points are within a work platform potential field. So if a certain number of work platform points are contained, we consider that field as attached correctly. But if not, we go to the next step to search for stair points below that field. So if there are stair points below that field, like the right figure over here, then that field is attached correctly due to regulation 2. However, if there's no stair points and no work platform points in that field, then that field is violating regulation 1. Similar to the former framework, now this framework is a process for checking regulation 3. So this time we check how many guardrail clusters are contained inside a guardrail potential field. So like the left figure over here, this number of clusters becomes the number of attached guardrails inside that field. So if that number is less than 2, then that field is violating regulation 3. But if that field has more than 2 or more clusters, then we go to the next step to check if the top guardrail cluster Z value is above 1 meter from the platform. And then we make the final decision about regulation 3. So for the results, we're going to show you two kinds of results. One is a segmentation result from RenDlanet, and the second result is a final result of the regulation checking process. So over here, you can see that we used F1 score for RenDlanet scores, and F1 score is a harmonic mean of precision and recall. And on the left figure over here, you can see a visualized predicted output of site D data from RenDlanet. And on the table on the right, you can see numerical F1 scores for each classes of site D data. So the highlighted colors on the class names match the visualized colors on the left figure. And using those predicted point clouds, we proceed to the regulation checking step and get these results. So on this table, you can see that work platform potential field 3 is considered to not have a work platform, but it has a stair points below that field. So that field is attached correctly. And you can see that on guardrail potential field 10 and 11, that our algorithm considered it as violating regulation 3. This is because on that field, there was only one guardrail attached. So as a result, we had retrieved 100% accuracy on checking the regulations of site D data. In conclusion, our study presented a fully automated methodology to accurately check major safety regulations for scaffolds. We could successfully divide a point cloud into 6 categories with an average F1 score of 62.7% using RenDlanet. And by developing a rule-based algorithm, we could check all considered regulations perfectly. So future works contain enriching the trained data set to improve segmentation results and generalizing the proposed method to other construction sites. These are our acknowledgements, and thank you for listening. If you have any questions or comments, feel free to ask. Yeah, you have a question? Oh, the mic's coming.
So when you reported the performance of the semantic segmentation method, yep, it says that the performance of the background class is the highest. And so my question is, when training the neural network, were you also training it to classify background points? And if that is the case, how did you overcome the imbalance in the data set? Because clearly the background class dominates the training data. And so what is preventing the neural network from just outputting everything as background and still achieving 90% performance?
Well, that is true, because our trained data set also had an imbalance on the background points and the other scaffold entities. And well, that was overcome because we used the transfer knowledge from the semantic 3D dataset, and that dataset also had more background points than other points, but it also had other points that were not background points, and that trained our initial layers of our neural network to overcome this, well, problem. I hope that answered your question.
So how does your model generalize across different scaffolding providers? Because clearly there are different providers that have different, materials being used, like Docker versus Perry or something like that. So have you tried them across different providers, or was all the data collected with the same provider?
So to be specific, do you mean by different providers like system scaffolds or door lock scaffolds?
Yeah, you have different brands. So the basic 3D structure of those brands are going to be entirely different, and the model is probably going to overfit to those 3D structures.
Oh, well, that's a good question, because, well, we showed only results on a one test data, and that could be a valid question. But after publishing this paper, we also, well, proceeded in our research, and we acquired some data from the construction sites that are very different to this data. It had like 7 floors of scaffolds. And well, our network, or our framework worked on that scaffold too. So we think it's robust enough to implement it on other scaffolds too. Yes.
Very interesting work. If you can please put that table that you were showing, the precision and recall with a picture, great, thank you. Can you share a little bit more insight on why bracing had a significantly lower precision and recall? Do you think it's more the type of data and the size of data they use for the purpose of training that made this impact, or do you feel like the method they're using, the way it models geometry and infers geometry, was not able to identify these diagonal components?
Well, first of all, we think that the reason of the low segmentation results of bracing is because of the lack of data of bracing class. Because in our trained data set in this paper, well, not including the background, there were only like 6% of the total amount of scaffold entities that were bracings. So it didn't have much data of bracings to capture the, well, bracing features, to let the RenderLiner capture the bracing features. And actually, after this paper, we proceeded, as I said before, and we enriched the data set and also modified the, well, parameters of the RenderLiner to effectively capture the geometry of the bracing. And we improved it to like 66%. So that was the main reason of the low segmentation results. Okay, thank you.
Thank you very much for this great presentation.